Pretty much
Alex, are you going to get coffee? Yeah. Okay, cool. Thanks. Oh, I'm stuck.
it's pretty much on the slide.
Except for the bar. Except for the party.
Yeah, some of the pathways were
What does it say? Inhibit.
inhibition. That's just me clearing things up.
Okay.
Basically, his arrows. Arrow means it activates when someone.
And means inhibit. Okay.
You can actually read it that way.
Okay. And the arrow means activate?
Arrow means activate.
Is it? Are you coming to visit him?
Yeah. Curious, just happy to stay.
Right.
Enjoy the weekend.
Yeah, I was stressed week, so I had like a submission to get to. And I was on that. But a really rough weekend. All done. Just, yeah. I don't know how there's such a like, oh my god, there's so many early submissions. When do you next submit?
Week 14.
What is it for?
That's for fucking nice. So sick of it. Research that.
Okay. So, the only submission we have is the
I think it's reasonably around that time.
okay.
You quick coming over that. How many was now?
To King's College?
Yeah.
No. But loads of people are apparently going. I don't
Yeah,
know.
I've set it all up.
Okay,
No, I
great.
just kind of like, there's like 12 of us.
Yeah.
And basically, on the email, if you want to read it, down the left, you know it's got
Yeah.
folders. For every event that we do,
You have a
you have
folder.
a folder.
Okay.
And you can send out memos to members, you know, the actual society.
Yeah.
If you go on there and go on mail, just click a box that says email or members. Just type it, which is everyone replies.
Oh, really?
So much better than posting. If you want to know something, do that. Send it to your email.
Okay.
Rather than personal one, so I think it's an
Official thing.
I got loads of replies saying not coming.
Right.
So we'll do that. And then I'm going to leave social. Josh.
Yeah.
Schedule.
Exactly. They'll have, I think, because they're also third years, I think that's why we haven't seen them.
Yeah. But at least setting up the social to mark that.
Exactly. They should be free after today.
I probably should have moved you, but I didn't.
It's okay. Right.
Otherwise, all good.
All good. Good to know.
The emails that you sent out to Radio Lollipop on the first day, I've just left this because it was kind of a conversation.
Okay, that's fine.
But, was it November time?
Yeah.
And I just, the first days or so, I'm not sure, because they emailed you, I had a look, and they said, do you want the scenario in the first day? I don't think that's what people say.
Yeah.
I don't know what it is. But actually what we found,
So they're going to do a scenario.
but other than that, it's cancellation society and wise maybe at some point. But that could be later on.
I actually went to, I had like a whole bunch of more emails that I had to send out.
It's fine. We've got this event. Once we have another social, we just need a couple more.
Yeah.
Some more socials.
Because it's nearly like volunteer.
Yeah.
October. When's Halloween?
Yeah.
It's going really, really quick. It's like,
Probably quicker than you.
yeah. How was your weekend? How was
It's weird. We actually left on Wednesday.
Oh, okay.
I had Thursday, Friday.
Oh wow.
So I had a pretty easy weekend. Which I'm sure you don't want to hear. But
Yeah. Did you do any work? No.
Yeah.
You did when you were in Venice. What did you do?
she's studying as well. So at times she's not actually in Venice, she's in like a city that's maybe like an hour on the train. So that's one day when I was studying the next day.
Just like,
It's pretty
yeah, I'm sure.
I'm going back for like a couple of days in 3 weeks. But after that, it was nice to get kind of through the travel.
Yeah.
Yeah, what's this thing going to be at 6 o'clock? Just
Oh, it's where all the societies come together, and then they just talk about grants and funds and
it's 2 hours with only people.
they do finish early most times, yeah, but it is a bit. It makes it a lot.
Did he delete it all, or did he like go?
I like to go and like test type it out, and then yeah, he just got it in. A few minutes to read it. Connor's dissertation.
It's just the initial.
Dissertation. No, they have like 3 types here. Like 3 weeks in, you have a project.
Oh, you were talking to him.
To be fair,
Yeah, similar. It's a boy who is this guy? Yeah, I know. Well, you're intrigued. I'm just curious what they're saying. Oh no.
Is Louise mother?
What do you think of this?
This one.
Or just the topic?
It sounds a lot more complicated than it actually is.
The intro and the
Right now.
I forget that bit. Why? Because it increases the live chicken. And then you meant to do full calls.
How are you finding your topic there?
Let's sit down and make a process.
Are you finding it
Quite a lot to
interesting?
remember. Avoid
And you do group post projects and stuff, do you? You do group posts and stuff? What did you have to do for that? Maybe they changed it.
You're right, I guess.
Because for me, we had to like do like a whole post presentation.
Let's start talking about diseases. I promised you diseases in this module, so I better start delivering. Right, we're going to talk about one of the most prevalent diseases in the developed world, which is also becoming more and more prevalent in the developing world. I do a bit about the basis of type 2 diabetes in level 2. If you take pathophysiology next year, we'll do much more about the current up-to-date research. I should mention that a couple of weeks ago I went to an international conference on type 2, well, on diabetes. So 90% of all people who have diabetes have type 2 diabetes. And this conference had 20,000 researchers at it. Okay? Lots and lots of people work on this. It's a major, major problem.
Are you talking today specifically about type 2?
I will talk about type 1 a bit. Type 1 is very simple. Type 2 is very complex. So I will talk about type 1 a little. Right. What is diabetes? Diabetes means loss of wee. Literally, that's what it means. It means an excess of urine. It was first identified in the 2nd century AD. It was named by a Greek, Areteus the Cappadocian, who was a physician in Alexandria in the 2nd century. And he identified 2 forms of diabetes, one of which is much more common than the other. Diabetes mellitus is more common. Diabetes insipidus is really quite rare. Diabetes mellitus is a metabolic disease. Okay? It's when basic cause is when you have excess blood sugar exceeds, this is, well, that's not cause of the disease. That's this is, if you like, diabetes mellitus is like a description of symptoms. It means an excess of sweet urine. How they found that it's sweet, I've got no idea. I don't want to think about that. But diabetes mellitus means an excess of sweet urine. The cause of this excess is because there's excess blood sugar, which exceeds the reabsorption capacity of the kidneys and causes water secretion due to osmosis. So glucose gets dumped in the urine, and that draws water with it effectively. The urine is sweet. It contains large amounts of glucose. I don't know how they found that out.
They did taste it.
I presume so. Diabetes insipidus is not a metabolic disease. It is a malfunction of the anterior pituitary gland. And it's absolutely nothing to do with what we're going to talk about today. It's worthwhile you know that it's there. You also get excessive water secretion, but the water is urine secretion. But the urine is very watery, insipid. And that's because it's a deficiency in ADH, antidiuretic hormone, which is responsible for water retention by the kidneys. If you have a deficiency in it, you have excess water dumped in urine. The urine is very watery and a large amount. The diabetes mellitus is what we're going to talk about. Diabetes mellitus refers to one of several disorders, not just 2, several disorders. But they are all basically caused by a deficit in insulin signaling. Either a lack of insulin production or insulin resistance. When we talk about insulin resistance, we mean there is still insulin, it binds to its receptor, but for some reason doesn't have the effect it should have. Our insulin plays many roles in energy homeostasis, so a lack of insulin signaling causes dysregulation of lots of areas of metabolism. So all of these symptoms are common to type 1 and type 2 diabetes, although the ones in blue are more common in type 1 diabetes. In many ways, type 1 diabetes is a more severe disorder than type 2 diabetes. We'll talk about that in a couple of slides. So, how many types of diabetes mellitus are there? There are at least 5, probably more. The two most important and most prevalent, probably 99% of all cases of diabetes, are type 1 or type 2. Type 1 is an autoimmune disease, destruction of the pancreatic beta cells by your own immune system. As we know, the pancreatic beta cells release insulin, therefore if you have type 1 diabetes, you do not have insulin. This is known as insulin-dependent diabetes sometimes. Although type 2 diabetes, people can also be insulin-dependent. Type 2 diabetes is a metabolic disorder. There are many different risk factors in type 2 diabetes. Some of them are lifestyle related, weight, diet, exercise. Some of them are genetic. Type 1 diabetes, most of the risk factors are genetic, some are environmental, lifestyle doesn't seem to play a big role. So both these disorders we call polygenic, because there are many, many different genes which can cause risk factors of getting them. There's no single cause of these diseases. There are risk factors. Gestational diabetes is normally a temporary condition caused by hormonal changes during pregnancy. There are similar risk factors to type 2 diabetes, for example, obesity. Maturity onset diabetes of the young and neonatal diabetes are ones I'll talk about at the very end. They are monogenic forms of the disease, single genetic mutations. These are the only forms of diabetes for which we can definitively say this is the cause. There are many different mutations which can cause this. But each person will only have one defined mutation. That mutation will cause the disease. Okay. Let's start off with type 1 diabetes. Type 1 diabetes, as I mentioned, is an autoimmune disorder where your body's own immune system destroys the beta cells of the pancreas. So it's a total absence of insulin production. The pancreas, as we know, normally releases insulin. Insulin lowers blood glucose levels by getting it taken up into the liver, the adipose, and muscle. So what happens when we have none of this at all? When we have none of this at all, we do not have any blood glucose uptake into any of these tissues, or very minimal. What we do get, because insulin inhibits glycogenolysis and gluconeogenesis in the liver, is the liver produces huge amounts of glucose. If you have no insulin in your blood, your body thinks you're starving, because insulin is secreted in response to meals, in response to high blood glucose. So no matter how much glucose there is in your blood, it could be 40 times the amount you normally should have there. If there's no insulin, your body will still think you are starving to death. Will do everything it can to increase your blood glucose level. So, glycogenolysis and gluconeogenesis will occur in the liver. The adipose tissue will metabolize and release their fats into the bloodstream. Your muscles will start to be digested. Proteolysis of the muscles will occur. This is the last-ditch attempt by the body to try to stave off death by digesting your own body tissues to produce energy which will keep your brain alive. Originally, when type 1 diabetes was first identified, the people identified it thought that all of your body tissues dissolved into your urine and were excreted that way, because people just waste away if they have untreated type 1 diabetes. Because the lack of insulin totally stops any anabolic reactions, any energy storing reactions, and all the energy releasing reactions are massively upregulated. The pancreas also secretes huge amounts of glucagon, because glucagon levels glucagon secretion is inhibited by insulin. So, the lack of insulin causes glucagon secretion. And that just makes everything worse. Because glucagon, again, tells all these tissues of your body to release as much energy as they can. Okay, so a total absence of insulin production causes all these problems. You also get a big reduction in ketones. Remember, ketones are a form of fuel your brain can use, which is derived from fats. Okay, they're only made in the liver. They're acidic, and they cause something called ketoacidosis, where your blood becomes very acidic because of all the ketones being produced. One of the symptoms of type 1 diabetes, people's breath smells a bit like hair drops. Hair drops smell the way they do because they contain ketones. If you have high levels of ketones in your blood, your breath will smell a bit of. Okay, so symptoms of type 1 diabetes. Lack of insulin signaling causes polyuria, so excess of urine, which in turn causes severe thirst and dehydration. This is an osmotic effect of large amounts of glucose in the urine. You get weight loss due to unregulated lipolysis and proteolysis. You get polyphagia, which is uncontrollable eating, which is the starvation response. Remember, you have no insulin, your body thinks you're starving. You get ketoacidosis, because your body thinks you're starving, so it produces ketones in your brain. Without external insulin application, type 1 diabetes is invariably fatal. Since the 1920s, we've been able to treat it quite effectively, since it was discovered that insulin secreted by the pancreas can reverse all of these problems. But as I said, you've got to be careful with the amount of insulin people take. If you take too much insulin, insulin does its job very well at lowering blood glucose. You lower it too much, and you get hypoglycemia, which can cause coma and death. What causes type 1 diabetes? Not entirely fully understood. We know that it primarily manifests in younger people. Generally speaking, if you're over the age of 30, you're past the point at which you are likely to develop it. Some people can develop it into their 30s. Most people who develop it at some point in their teens. And it results in autoimmune destruction of the pancreatic beta cells. Here's the pancreas, these little dots of pancreatic islets. Here's an islet. The red cells are the beta cells. We know all about those. They're insulin. There are many genetic factors. There are some environmental factors, so drugs and toxins can cause an increase in the incidence of type 1 diabetes. Some diseases, some viral infections are known to trigger type 1 diabetes. So there are more than 50 genes associated as risk factors with type 1 diabetes. No single one of these causes type 1 diabetes, but they are risk factors. If you have this genetic variant, you are more likely to get it. 40% of people with familial type 1 diabetes have mutations in MHC genes, major histocompatibility complex, part of the immune system. I'm sure you'll cover these a lot in your immunology lecture. 30% of all type 1 diabetes patients are heterozygous for this particular allele. So this particular MHC2 allele gives you an increased risk of type 1 diabetes. Just because you have it doesn't mean you're going to have type 1 diabetes. 70% of people with type 1 diabetes don't have it at all. So clearly it's the cause, it's a risk factor. Genetics is really complex. We know it's complex. We know it's not simple. Because identical twins only have a 30 to 50% coincidence of type 1 diabetes, and identical twins are genetically identical. Unlike something like yes. Acute pancreatitis can certainly cause type 1 diabetes. Because acute pancreatitis, you digest your own pancreas, which is very nasty. Generally speaking, acute pancreatitis, if it's untreated, is fatal within hours. If you survive it, you may well have type 1 diabetes, but you probably just have to be alive. Chronic pancreatitis may well, I'm not really certain. But it seems largely unrelated to lifestyle. So drinking loads and loads of sugar doesn't give you a greater risk of having type 1 diabetes. It doesn't seem to depend too much on ethnicity. Potentially it could be triggered by a viral infection, but we don't really know. As I said, acute pancreatitis can also destroy beta cells, and some chemotherapy agents. So streptozotocin, for example, destroy beta cells. Things used in cancer treatments. Okay. So that's type 1 diabetes, which is in essence a pretty simple disease. The causes of it are probably quite complex, the genetics of it are quite complex, but in terms of why it has the symptoms that it does, fairly simple. It cannot produce insulin. And you can see from this example how the absence of one signaling molecule in your body causes all these catastrophic effects. Thankfully, because it's only the absence of one signaling molecule, we can treat it by externally applying that molecule. Yes?
For example, if it was a viral infection that started the process,
yeah.
If that was treated, would you be able to reverse it? Or it got too bad?
I'm not certain about that. I'm not an immunologist, so that's a difficult one to answer. I think if you treat viral infection, you are treating. There aren't that many drugs to start off with to treat viruses, which kill viruses. But if you treat viral infection, you're still going to have the immune response. And it's almost like the virus hypersensitizes your immune system. And for some reason, it then goes on to attack the pancreatic beta cells. So I don't know at what point you could stop it, halt it. So I can tell you that the destruction of the beta cells by your immune system is totally painless. You don't know what's going on. So if somebody has a viral infection, you probably wouldn't realise it's happening. Also, you can lose about 90% of them before you have any symptoms of type 1 diabetes. So whether or not that would be a viable way of stopping it, I don't really know.
Tim,
yes.
if that's the case and they believe it's a viral infection, have they pinned down the virus?
It may be a virus. Maybe.
Yeah, but for somebody to suggest that, have they got an idea of which
It's
virus
possible
it may be?
because this is probably it's probably not a particular virus. This is probably because they found an association that a certain percentage of people who develop type 1 diabetes can recall having a severe viral infection 30 days earlier or something like that. Yeah, it's probably not that they've actually seen it happen. It's probably they've associated it with that. It's a bit like things like ME, that people who get ME generally, a certain percentage of them can recall having an acute viral infection preceding it. So it's an association.
Yeah.
We have to be careful with associations, which I will discuss a lot in type 2 diabetes, actually. There's a lot of associations made. Associations aren't generally scientifically sound evidence. Right. Type 2 diabetes. 90% of all people with diabetes have type 2 diabetes. This has been described by some as the scourge of the Western world. But it's not just the Western world that's the problem. The biggest rise in cases of type 2 diabetes are in countries whose economies are currently booming. So countries what are sometimes referred to as developing countries, or BRICS, Brazil, Russia, India, and China. And now we've got the MINTS as well, which is, I can't remember what M stands for, Mexico, Indonesia, Nigeria, and Turkey. In all of these countries where their economies are developing very fast, type 2 diabetes is also increasing very quickly. Okay, so what is type 2 diabetes? It's much more complex than type 1 diabetes. We have an intact pancreas still, initially at least. Insulin is still secreted, but certainly later on in type 2 diabetes, the levels of insulin are reduced. What we do know is that insulin-responsive tissues become insulin-resistant. So muscle, adipose, and liver don't respond to insulin in the blood the way they normally do. And there's a big spectrum of severity. Initial symptoms are generally mild. People often do not go and see their GP until they've got quite severe symptoms. And there are many, many genetic and lifestyle factors. Classically, we associate type 2 diabetes with people who are older and people who are overweight. And these are certainly major risk factors. Hence the sedentary lifestyle, smoking, high blood pressure. So that gives us the question. Does obesity cause type 2 diabetes? And this is a question which is debated in the press an awful lot. What do you think? We're not making any value judgments here. Who thinks, based on what they know, that the major cause of diabetes is obesity?
Possibly.
Who thinks that it isn't? Okay, interesting. Okay. So most people don't want to commit one way or the other. Yes?
Must be like a risk factor on the cause.
Yeah, I would say it's a risk factor, but it's not as simple as it seems. It's certainly a risk factor, but it's not as simple as it seems. The reason why it's not simple is because of the cell signaling pathways involved, which is why we choose diabetes to illustrate this. Okay, so let's have a look at the data. More and more, we are going to want you to examine scientific data and come to conclusions based upon it. This data is crystal clear. There is a correlation between the increase in obesity and the increase in type 2 diabetes. Increase in type 2 diabetes and the increase in mean body weight in this decade between 1990 and 2000. And you could extend this further on to go up to the present day. Mean body weight is still rising. Levels of type 2 diabetes are still rising. Currently, type 2 diabetes treatments consume 10% of all the money spent in the NHS in this country. And that's predicted to go up to 17% in about 20 years. This is billions and billions of pounds every year. This is why it's so important we understand why it's happening. So there's a clear correlation here. Diabetes prevalence goes up, directly in line to mean body weight goes up. So this is a direct correlation. Therefore, obesity causes type 2 diabetes. Yes? It's all very clear. Do you think this is suitable evidence?
No.
Is this proof?
No.
You don't think it's proof?
No, because it could be your microbiome, it could be an introduction to a new food group.
But you're just saying other things. This is the data. This is what we're seeing. This is the
That's one
correlation.
set of data. There isn't more to compare and contrast.
Absolutely. Yes. 1994. No, it doesn't. That's an outlier. We're always going to get outliers, but yeah, okay. Right, so few people are skeptical of this data. You should be skeptical of correlated data. Newspapers love this sort of thing. It grabs loads of headlines. You should always be skeptical about correlations. I'll show you a few other ones. Organic food causes autism. This is absolutely crystal clear from this graph. Organic food sales go up, autism goes up. This is actually correlated better than the rise in diabetes and the rise in obesity. Don't get that one in the Daily Mail, do you? Organic food causes autism. Okay. Do you think that's true? Says it here. Direct correlation. How about this one? Margarine causes divorce. Divorce rate in Maine per 1,000 people, per capita consumption of margarine. 99% correlation. Better than the correlation between rise in obesity and the rise in diabetes. Margarine's rank, so I can see why it might cause divorce. Butter is much, much better. However, this is clearly rubbish. What other correlations have we got? Nicolas Cage makes people drown. Good correlation. Number of films Nicolas Cage is in per year, number of people who drown in swimming pools. Correlates quite nicely. There's also a direct correlation in the average height of Miss USA and the number of people in the USA killed with steam irons. Always be careful of evidence. Always question it, okay? So, on the basis of that, we've talked about obesity as type 2 diabetes not having a cause. It has risk factors. So I've got two guys here. Olympic cyclist or the man on a sofa? Which of these is more likely to get type 2 diabetes? Not who is going to get type 2 diabetes, who is more likely? Right, who thinks A? Who thinks A? Right, most people. Who thinks B? Nobody thinks B? Right, okay. This is again where you have to know all the facts. The answer is B, not A. Not because Olympic cyclists get type 2 diabetes. Can you see how thin this man is? He's actually a Paralympic cyclist. He has a condition called a lipodystrophy condition. And the discovery of people like him, there are only 8 of them in the world with this condition. Yeah, not many, only 8. Totally turned the thinking about type 2 diabetes on its head. This guy has risk factors for type 2 diabetes. Sure, if he spends all the time on the sofa eating pies, he's more likely to get type 2 diabetes than somebody who has a healthy diet and lifestyle. However, this man has no body fat whatsoever. He has a genetic mutation whereby he has no fat. And every single one of the people in the world who has this mutation has type 2 diabetes. If you take a mouse and you give it this mutation, so the mouse has no body fat, it has type 2 diabetes. So clearly, it's not fat that causes type 2 diabetes. It cannot be, because these people are not fat. And they all have type 2 diabetes. So what on earth is going on? So, we know there's a link with obesity, but it's not simple. Many obese people do not have type 2 diabetes. Some people with healthy BMIs have type 2 diabetes. We know that waist circumference, especially in men, is a better measure of risk of type 2 diabetes than overall body mass. But still, we don't know. Some ethnic groups are more susceptible than others. That's a key factor. People of the same ethnic group share more genetics than people of different ethnic groups. Therefore, you must assume that there could be a genetic factor. Let's have a look. Different prevalence in different countries. This is the increase in type 2 diabetes between 1980 and 2014. In Europe, it's gone up a fair amount. But look at how much it's gone up in Africa, Southeast Asia, the Western Pacific. These are areas where the economies have massively boomed in this 34-year period. And for some reason that I don't understand, when countries get rich, everybody starts eating McDonald's. You have to pay. Sorry, somebody have a comment.
That's a convenience.
Convenience, maybe, yeah. So, generally, as countries become more wealthy, they start to migrate to a Western diet, a more high-fat diet. But it seems that in some countries it's worse than others. Why is that? If you look in Europe, this increase in type 2 diabetes in the last 34 years is relatively modest. But if you look in the Middle East, it's double. So, type 2 diabetes and ethnicity is a very interesting question. Now, you have to be very careful with any data based on ethnicity. The reason why is because not all ethnic groups have the same lifestyle. And not all ethnic groups have the same socioeconomic status. At least in this country, in the United States, there's quite a polarization. So this, again, is information which is useful, but should be taken with a pinch of salt. So if you standardize all the results for, this is in the UK, for ethnic groups, if you standardize them based on age and sex, you see that per 100 people, the white population of the UK, 1.7. The African Caribbean population, 5.3, all South Asian, 6.2, Indian or African Asian, 4.7, Pakistani and Bangladeshi heritage, 8.9, Chinese, 3. So these are the relative numbers of people, percentages of people, these ethnic groups who have type 2 diabetes. But there's a clear difference in ethnic groups. Again, maybe this is genetics, but it could also be lifestyle. So how do we unpick this? Well, this is quite an interesting graph. Unfortunately, very difficult to see. Quite interesting. Right, okay. So this is showing us, this is women on the left and men on the right. This is showing us the average BMI somebody has to have a 50% increased risk of getting type 2 diabetes. Okay. So, for white women and for white men, you have to have a BMI of around 30 to get an increased risk of type 2 diabetes. However, for example, black women, it's 28, Chinese women, it's 24, South Asian women, it's 22. Similar trend with men, although slightly different. So what does this mean? This means that certain ethnic groups, obesity is a greater risk factor in diabetes.
Could that possibly be because for centuries we've been used to our diet and it's been introduced not slowly but slow enough, whereas a South Asian
We might have evolved to cope.
Yeah.
Yeah, well, certainly there is there's a good example of that actually. So one ethnic group is not on it, because there aren't that many in the UK, are indigenous Inuit populations who live in the boreal region, so northern Russia, northern Canada, and these populations tend to exist on a very, very high fat diet because they eat a lot of seal blubber. Okay, very high fat diet. There aren't many of these people left. And yet they don't have very high incidences of type 2 diabetes.
But they do, oddly enough, in northern Canada, where they're drilling for oil, where the money has been introduced.
Interesting. Difficult question. I'm not saying I have all the answers. There's another interesting thing as well. There is one group of people who are all morbidly obese, and none of them have type 2 diabetes, and those are sumo wrestlers. So professional sumo wrestlers, while they're still training, do not have type 2 diabetes. They're all massively overweight. But clearly not just obesity. Right. There's also a link with socioeconomic status. There's a higher incidence of type 2 diabetes in deprived groups. These are deprivation fifths. So this is the least deprived group. This is the most deprived group socioeconomically. We know that there is a big difference in lifestyle between these groups. And it's possibly something to do with that. There might be other reasons. We don't know. Lots and lots of correlations. Okay. So let's have some actual science and work out what's going on. Does fat cause type 2 diabetes? No, it's a risk factor. Many people with type 2 diabetes have what we know non-alcoholic fatty liver disease. Excess fat deposits in the liver. 80% of obese people have non-alcoholic fatty liver disease. Many people with type 2 diabetes also have fat deposits in their muscle. And people with excess visceral fat are more likely to have type 2 diabetes, so more fat around the stomach, which is why men are more likely to get it than women, because men tend to carry their fat around their stomach. We also know that an excess of free fatty acids in the blood are linked to insulin resistance. So what does all this mean? So remember, as well as people who are clinically obese having lots of subcutaneous fat, sort of fat you can see, looking like here, they have these fat deposits in their liver and their muscle as well. What we think is it's not the amount of fat, but how it's stored. In a certain sense, subcutaneous fat, the sort of fat you can see, the sort of fat we all try to lose, is your friend metabolically. This is a safe store of fat in your adipocytes. We know that if we take that on mouse, that mouse with a leptin deficiency that eats until it is morbidly obese and gets type 2 diabetes, we know if we give that mouse another mutation that makes it increase the number of fat cells it's got, that mouse becomes metabolically healthy. So even though it becomes fatter, it becomes healthy. So storing fat in adipocytes is what we're supposed to do. Yes?
Where you get the concept of a skinny fat person.
What? Somebody who's fat but metabolically healthy.
Yeah,
It
so
is
like
fat
you look like a skinny, healthy person.
Oh, I
but
see what you mean.
actually inside you're carrying a lot of fat that shouldn't be there.
That is exactly the problem we think is occurring with this person here. So once your storage in adipocytes is exceeded, what we think happens is the excess fat can't go into adipocytes anymore where it's safe, where it can be safely stored, but it goes into pancreatic beta cells, it goes into muscle cells, and it goes into adipocytes. And this is where it causes problems. And the reason we think that there is a difference in different ethnic groups and different genetic subtypes of people is that some people simply have a greater capacity to store fat in their adipocytes than others. And when that storage is exceeded, that is when you start to get the problems. Healthy fat is good for you. But when you get too much fat going into it, you damage these adipocytes, you reduce their ability to store fat. And the fat goes to other places. How does this happen? Well, this has given rise to the term lipotoxicity. Toxicity, poisoning by fat. So you know that long-chain, unsaturated fatty acids, if you take some pancreatic beta cells on a dish, if any of you do your level 3 project with me, you'll do stuff like this. You grow pancreatic beta cells in a dish, and I stick some saturated fatty acids on those beta cells. They will no longer release insulin properly in response to an increase in glucose. So we know that unsaturated fatty acids inhibit insulin secretion. We also know that they cause insulin resistance in muscle cells. So once the capacity for fat storage in adipose tissue is exceeded, we think these free fatty acids accumulate in the bloodstream, get into the muscle cells, the pancreatic beta cells, and the liver cells, and cause a lot of the symptoms of type 2 diabetes. The problem that this guy has is because he has absolutely no fat cells, he can't store his fat at all. So any fat that he has in his diet is going to end up in his blood looking for a home and going into all the wrong places. And interestingly, an interesting aside is it seems that unsaturated fatty acids are protective to pancreatic beta cells and to muscle cells. Saturated fats you find in things like butter.
Is that a typo then? Because you've got the unsaturated fatty acids.
Oh, sorry, that is a typo. God, what am I talking about? I thought that sounded wrong when I was saying it. Thank you, Grace. Good job. What is this? Saturated fatty acids inhibit insulin secretion. Let's change that right now. Let's change that right now. Can't believe nobody last year spotted that. So, saturated fatty acids inhibit insulin secretion. If I take saturated fat and I put it onto pancreatic beta cells or skeletal muscle cells, it will inhibit insulin secretion. Sorry, saturated fatty acids will inhibit insulin secretion in beta cells. They'll inhibit insulin action in muscle cells or liver cells. They'll cause insulin resistance. But unsaturated fatty acids seem to be protected in situations. We don't quite know how that translates to diet advice to people. We do know that people who have a diet high in oily fish and olive oil seem to be metabolically more healthy than people who have a diet high in dairy products and animal fats. How what we see in a test tube relates to what we see on in a person is difficult to reconcile. So let's take these one at a time. So we said saturated fat inhibits insulin secretion. Let's talk about that. How does that occur? Well, there are two ways. Firstly, it can actually kill the beta cells. If I take beta cells in a dish and stick saturated fat on them, palmitate, for example, a lot of those cells will die. The question is, how does that happen? By inducing what we call apoptosis. Apoptosis is programmed cell death. Cells, when they become really stressed, they effectively commit suicide. Programmed cell death. It's a very neat way of the cell packaging itself up and being digested by macrophages. And that stops the cell just bursting open and releasing lots of toxins. So we know long-chain saturated fatty acids, like palmitic acid, when they're taken up into a beta cell, they go into peroxisomes, and they produce hydrogen peroxide. Hydrogen peroxide is a really potent cell stressor, oxidative stress in the cell, and can trigger apoptosis. Now, Heather McDonald is going to talk to you about apoptosis in her lecture, so I'm not going to go into any more detail on that. But saturated fatty acids can directly kill macrophages. But at a level below that acute toxicity, they can inhibit insulin secretion in the cells. We don't fully understand how this happens, but we think it's something to do with ion channels. So we think, for example, saturated fatty acids, so you know this diagram well. So we need two things to happen for insulin to be secreted. KTP channel has to close, calcium channels have to open. We think saturated fatty acids inhibit the closure of the KTP channel. We also think that they cause a problem with calcium channels. Normally, calcium channels exist in these nice tight clusters on the membrane, close to the secretory granules. So when the calcium floods in, it binds the granule, or synaptotagmin on the granule fuses with the membrane and insulin is released. If these calcium channels, instead of all being localized near to these insulin secretory granules, are dotted randomly all over the cell surface, there won't be this big coordinated influx of calcium. The insulin secretion will not be triggered properly. But we don't fully understand why this occurs. Insulin resistance is probably the first problem that occurs in type 2 diabetes. And this is a lack of normal insulin response from insulin-sensitive tissues. The liver, the skeletal muscle, the adipose tissue. So this is a very simplified diagram taken from the Diabetes Charity website, showing you insulin being the key in the cell that opens this channel that allows glucose to go into the cell. We discussed it's not exactly like that. Insulin binds to its receptor on the surface, causes translocation to the surface of a GLUT4 protein, which allows glucose into the cell. For some reason, in type 2 diabetes, although there's still insulin there, insulin still binds to its receptor, but for some reason, it doesn't have the action it should. It doesn't cause glucose uptake. The insulin is the same, it's not changed. The receptor is the same. So what's going on? And we think again it's because of fat inclusions inside muscle cells and liver cells. So we know, for example, mice that on a high-fat diet develop obesity and insulin resistance. Now this correlation, this insulin resistance, if you measure the insulin resistance occurring and the obesity occurring in mice, they don't correlate directly. Insulin resistance correlates directly with the increase in diacylglycerol in the muscle. So free fatty acids in the blood, and if you're overweight, you have a lot of free fatty acids in the blood. They go in to your cells, muscle and liver cells, okay? And they can get metabolized diacylglycerol or ceramide. Diacylglycerol is the first stage on the pathway to triacylglycerol synthesis. Triacylglycerol is what we generally refer to as fats. Diacylglycerol, as you might remember from our previous lecture, is an important second messenger. It's a signaling molecule. Ceramide is also signaling. So how does this interfere with the insulin signaling pathway? little reminder, what does diacylglycerol do in your cells? So, G protein comes to the receptor, a signal binds to the outside of it, activates G alpha Q and beta gamma. G alpha Q and beta gamma activate phospholipase C. Phospholipase C phosphorylates PIP2, cleaves PIP2 into IP3, inositol triphosphate, and diacylglycerol. This is a normal signaling pathway, okay? This is what normally happens. IP3 causes calcium to be released from intrapassive reticulum. Diacylglycerol binds to protein kinase C. Protein kinase C also is activated by calcium. Okay? Right. However, this is a normal signaling pathway. We covered this in the last lecture. Some protein kinase Cs only need diacylglycerol to activate. So this excess diacylglycerol is occurring in the muscles, liver, of mice, or people, excess free fatty acids in their blood. It's going to activate a form of protein kinase C called novel PKC. Why is that for? Okay. So we know that in the muscles, which should be responding to insulin, novel PKC is going to be overactive. Let's remind ourselves of the insulin signaling pathway. Insulin binds, receptor dimerizes, receptor phosphorylates, IRS1 is recruited, that recruits PI3 kinase. PI3 kinase makes PIP3 out of PIP2. PIP3 recruits PIP3 dependent kinase and AKT. PPK phosphorylates AKT to activate it. PIP3 is degraded to PIP2 by P10. And AKT goes on via this pathway to activate the translocation of GLUT4 from these vesicles to the membrane, allowing glucose to come into the cell. That's the normal insulin signaling pathway that occurs in metabolic healthy individuals. So what happens in this pathway when we overactivate novel protein kinase C because of our excess intracellular diacylglycerol? Novel protein kinase C also phosphorylates a component of this pathway. When it's activated by diacylglycerol, it phosphorylates IRS1 and inhibits this section of the pathway. It phosphorylates IRS1 and stops it from recruiting PI3 kinase. Once you have inhibited this part of the pathway, once PI3 kinase can no longer be recruited by the insulin receptor, none of this downstream stuff is going to happen. So it doesn't matter how much insulin is binding to this receptor, you are not going to get any GLUT4 translocation to the surface, you're not going to get any glucose uptake. Ceramide, being a product of lipid metabolism as well, so excess lipids in your muscles are going to cause an increase in ceramide levels, activates protein phosphatase 2A. Phosphatase is the opposite of a kinase. Kinase puts phosphate onto a molecule, onto a protein. Phosphatase takes that phosphate off. What does protein phosphatase 2A do? Dephosphorylates AKT. It takes that phosphate off AKT, which means that AKT is inactivated. Even though insulin is bound, even though this part of the pathway is active, AKT is dephosphorylated and inactivated, which means that no GLUT4 is going to go to the surface, because AKT activation is required. Okay. That is, in principle, how we think insulin resistance arises from fat accumulation in muscle and in liver. Does anybody have any questions about that? These are pretty key points I want you to understand. So if anyone's got any questions, please ask them. Okay, all clear? Excellent. You get a kind of a vicious circle of insulin resistance. If you remember, there's insulin receptors in your fat cells as well. Your fat cells have these lipid droplets, and these lipids are liberated by hormone-sensitive lipase. Hormone-sensitive lipase is inhibited by insulin. Okay. So if your insulin signal is not working because you've got this increase in free fatty acids in the blood, increase in diacylglycerol ceramide inside your adipocytes. Instead of these things being stored safely in these lipid droplets, they're inhibiting insulin receptor. That stops the inhibition of hormone-sensitive lipase, which means hormone-sensitive is overactivated. Okay? So this inhibition no longer happens. HSL is overactivated, which causes the liberation of excess free fatty acids into the blood. So insulin resistance increases the amount of free fatty acids in the blood. So it increases its own, the insulin resistance effectively increases insulin resistance. Makes insulin resistance become worse. What we think happens in type 2 diabetes is people initially have insulin resistance and a small level of insulin resistance. And what does your pancreatic beta cell do? It increases the insulin secretion to try and overcome this. As your insulin resistance gets worse, eventually your pancreatic beta cells can no longer secrete enough insulin to overcome that resistance. That's when the symptoms of diabetes become apparent. It's also true that at some point the levels of fats building up in the pancreatic beta cells give you failure of those pancreatic beta cells, and so the insulin stops being secreted properly.
Is that the point where it becomes irreversible?
That's a very interesting question. There's a lot of debate about when type 2 diabetes can be reversed. What we do know is that within 10 years of diagnosis, for most people, about 80-90%, if you lose 15 kilos of body weight, your type 2 diabetes is pretty much reversed. Within 10 years of diagnosis.
Does that matter what size you were before you lost the weight, or is that?
Well, that depends. I mean, obviously, if you're one of these unlucky people who gets type 2 diabetes without really gaining any body mass, then, yeah, you probably won't need to lose as much. It will be proportional.
Yeah,
but,
yeah.
But the thing is that this research was done on people going into gastric bypass surgery. And all people with gastric bypass surgery to be considered for it has to be more than this. So 15 kilos is the amount of people with BMI over 30.
So, say if you lost about 15 kilos in a really short amount of time,
Yep, that's the best thing to do, actually.
then, well, yeah, but rather than over 10 years, it's saying that, say if you lost it in like a year, the same that you wouldn't have type 2 diabetes anymore.
A lot of the effects will be reversed. I'm not going to say. What I can say is that we do know that pretty much everybody who's got type 2 diabetes, who's lost a significant amount of weight, got down to a normal BMI or a low level of a normal BMI, within a certain period of being diagnosed, their type 2 diabetes has been reversed. Which is interesting, because we spend 10% of the NHS budget on this disease, it's free to cure. But losing weight, as I'm sure everybody appreciates, is much easier said than done.
That's another interesting thing, because to have a gastric bypass, you need to lose some weight.
Yeah, well, and that's another reason why gastric bypass surgery is very effective. People actually have to go on a 6-day starvation diet before gastric bypass surgery. It's thought that even that 6 days of starvation, meal by mouth, is enough to get your pancreas working again and to reduce your insulin resistance. Right. Insulin signaling the liver, similar to muscle. Increased free fatty acids, increased diacylglycerol ceramide. So if we activate novel protein kinase C with diacylglycerol, we inhibit that part of the signaling pathway. If we activate PP2A with ceramide, we inhibit AKT, that part of the signaling pathway, and it means that the liver, instead of making glycogen out of the glucose in the blood, because when insulin is secreted, the liver starts liberating its own glycogen stores and making new glucose by gluconeogenesis. And that exacerbates the hyperglycemia. So it works in a very similar way to in the muscle. You must remember that most of the reduction in blood glucose caused by insulin is because of glucose uptake in the muscle. But the liver is the major regulator of your metabolism in terms of gluconeogenesis, glycolysis, various other things, glycogenolysis. So if the liver's producing too much glucose, generally speaking, you're going to have a high blood glucose level. Right, so insulin resistance is it caused by circulating fat, caused by a free fatty acid buildup inside the liver and muscle cells, caused by large amounts of subcutaneous fat, or is it caused by excess blood glucose? Who thinks A? I can understand why you might say A. The answer's not A. Who thinks B? Who thinks C? Who thinks D? Good, I'm glad most of you got that right. We think it's because of B. Current thinking is because this is the reason why. And remember, it's the inhibition of the signaling pathways that I talked about in the last lecture that causes this insulin resistance. Okay, what does insulin resistance do? Who thinks that it causes increased lipolysis? Who thinks that it causes increased glucose uptake? Decreased glucose uptake? Who thinks it causes increased glucose released by the liver? Who thinks it does all of these things? Nobody thinks anything. The answer is all of them. Insulin resistance. Because insulin, remember, normal insulin signaling decreases lipolysis, increases glucose uptake, and decreases glucose released by the liver. So if your cells are insulin resistant, they will not do these things. And so your rate of lipolysis will go up, your rate of glucose uptake will go down, and glucose released by the liver will go up, which means that you will have hyperglycemia, hyperlipidemia. And early on in type 2 diabetes, hyperinsulinemia, very, very high levels of insulin circulating around the blood. And that probably causes a lot of other problems. For example, some of the things that occur in type 2 diabetes are increased risk factors of getting Alzheimer's disease and osteoarthritis, possibly due to high levels of insulin. Right. Intracellular free fatty acids inhibit insulin signaling by what? Do they stop insulin binding its receptor? Do they block glucose trafficking to the membrane? Do they bind to the insulin receptor? Do they create second messengers which inhibit the insulin signaling pathway? Who thinks A? Who thinks B? You? Who thinks C? And who thinks D? Everyone's being very tentative. I'm not judging you. I think you're clever if you put your hand up at all. Right, okay. Not many people wanted to take a punt on that. Now, the answer to this is complex. The answer to this is actually D. Right? It does block glucose trafficking to the membrane, but by inhibiting the insulin signaling pathway. So diacylglycerol is a second messenger which inhibits the insulin signaling pathway. Okay. So insulin resistance in a nutshell. Increased glucose release by the liver, increased fat release by adipose tissue, decreased glucose uptake by liver, fat and muscle. And it's this lack of insulin action that causes a lot of the problems in type 2 diabetes. Remember, a lot of people who have type 2 diabetes have a lot of other complications as well, and some of that is caused by obesity, which is not necessarily related to this. Things like arteriosclerosis. Right. Which is more important? That's the question. We don't know whether insulin deficiency or insulin resistance is the main factor in type 2 diabetes. But one model is that high circulating levels of free fatty acids cause insulin resistance. And pancreatic beta cells then release more insulin to compensate. Diabetes becomes apparent when insulin secretion can no longer compensate for insulin resistance. If you think about what I was saying earlier about this idea of losing small amounts of weight to cure type 2 diabetes, think about you have this reservoir in your body, your fat reserves. This is a safe way of storing fat. Okay? And when that's filled up, so let's say this water bottle, fill it up with water, right? This is fat, imagine this is fat in here. When that's filled up, that water's still safe. However, when you try to put more in, it spills over the edge, it splashes on the floor and gets the shoes wet. At that point, the analogy breaks down. But the point is that it's safe when it's just going into the store that's meant to store it, the adipose tissue. When that store is exceeded, small amounts of fat, we are talking small amounts, end up going into your pancreas, your muscle, and your liver. And it's been estimated. So in order to, and this is what causes the pathology of type 2 diabetes. So in order to reverse that pathology, all you have to do is lose that excess bit of fat that has gone into the other places. And it's been estimated that it's as little as half a gram of fat in your pancreas that can cause type 2 diabetes.
Can I ask, is that the first fat that you lose as well?
Probably not. But you will lose it at the same time as the stuff in your stores. The trick is, if anyone here is unlucky enough to develop type 2 diabetes, do something about it early. Because this progressive damage keeps happening. And it becomes more and more difficult to do something about it as you progress through type 2 diabetes. Eventually, your pancreas is defunct, your fat cells will inflate, your liver is damaged, you get liver steatosis, you get liver cirrhosis, and you get irreversible damage. Okay. The question is, though, is dietary fat actually the main problem? I've talked about, being very specific, to talk about circulating fat levels, fat in your muscles, fat in your liver. But is it just the fat that we eat that is causing this problem? And there are some clues in this. In some experiments that are done. We know that rats fed on a high fructose diet become diabetic before they become obese. The question is why? So fructose is a sugar. Quite similar to glucose, it's a monosaccharide. It doesn't get metabolized in the same way. Fructose is sweeter than glucose. It's sweeter than normal sugar. And because of that, it's used as a sweetener in a lot of processed foods, particularly sweetened fizzy drinks, things like Coca-Cola. Other colas are available. And one of the things that has been observed in people in countries where type 2 diabetes is becoming increasingly prevalent is more and more stuff like Coca-Cola, sweetened fizzy drinks is getting consumed. Again, that's a correlation. Okay, it's a correlation. We know about the risks of correlations. But there does seem to be some link between fructose consumption and the development of type 2 diabetes. And why might this be? So fructose is metabolized in a different way to glucose. Mostly in the liver, some of it's metabolized in the muscle, but mostly in the liver. Fructose metabolism is biased towards glycogen replenishment and lipolysis, whereas glucose metabolism is all about making more ATP. Fructose metabolism, when fructose is metabolized by your cells, it goes towards storing energy. Many products are high in fructose. High fructose corn syrup is a very cheap way of sweetening. We know if we give high levels of fructose to rats, they become diabetic. You know, if people have a lot of fructose, they seem to have a higher risk of diabetes. What we think happens is the excess dietary fructose is converted into hepatic and muscle fat deposits. So it might not be making you overweight, although certainly drinking too much highly calorific fizzy drinks will make you overweight, but it can cause insulin resistance because it's not adding to your subcutaneous fat, but it is adding to your fat deposits in the muscle and the liver. As we discussed, these are the fat deposits which cause the inhibition of the signaling process. We refer to fructose quite often as a lipogenic sugar. This is the metabolic pathway, don't worry too much about it, but as you can see here, fructose is metabolized to fructose 1-phosphate by fructokinase, and via a lot of different pathways can end up going down to triglycerides and fatty acids. So if you give fructose to a rat, you see increase in lipogenic genes in expression in the liver. There's probably some sort of evolutionary reason for this, but I'm not really sure what it might be. But we haven't evolved to ingest very high levels of fructose. So this is something your body is not built to cope with. You can get ATP depletion. And unlike glucose, the levels of fructose in your blood are not regulated by insulin. Okay? Fructose does not trigger insulin release. So what's the other outcome of that? What do we know about insulin? Besides lowering blood glucose, what does insulin do to your appetite? It makes you feel full. So if you're taking on a huge number of calories by way of fructose, but fructose doesn't trigger insulin release, you're not going to feel full, so you're going to consume more calories. Now, I would customarily take a break at 4 o'clock, but there's not a huge amount of this lecture actually left. So I'm going to give you guys the choice. Do you want a 10-minute break, then we'll have another 20 minutes? Or do you want to plow on through and finish a bit early? What do you want to do? Who wants a break? Hands up if you want a break.
Just me then.
Hands up if you want to stay. Sorry, Grace, you're overruled. Right. Okay. So now we know what's caused this train wreck. We know what's damaged your metabolism. So what do we do about it? How do we treat type 2 diabetes? And actually, we're not very good at treating type 2 diabetes with drugs. All we ever do is treat symptoms, not the cause. Partly because we don't fully understand the cause, and partly because the cause is very difficult to treat, unless you can persuade people to lose weight. So one of the first-line treatments of type 2 diabetes is sulfonylureas. They're not actually used that often these days. They used to be used a lot more than they are now. One of these is glibenclamide. And what this does is it directly blocks the KATP channel, independent of ATP. So this is our little diagram of insulin release KATP channel. Causes beta cell depolarization, causes calcium influx, which causes insulin secretion. I'm sure you're all seeing that. This doesn't happen properly in people with type 2 diabetes. They're not releasing enough insulin. So if we can give them sulfonylureas, what that is, they block the KATP channel directly and cause insulin secretion. So this will increase insulin release. Won't do anything about insulin resistance though. Also, treatment by sulfonylureas ceases to be effective within a few years, about 50% of patients. And you have the risk of overdose. Take too many sulfonylureas, you use too much insulin, you get hypoglycemia. That's really bad. So that's one treatment of type 2 diabetes. Metformin is the most commonly prescribed type 2 diabetes treatment. We've known about metformin for 60 years. One of the most widely prescribed drugs in the Western world. We have absolutely no idea how it works, despite 60 years of research. But we know it does.
Find out it works.
It's the extract of a plant in which found people get taking this plant had some relief in their symptoms of hyperglycemia, and found
You
out
stumbled
that
upon it.
that's how a lot of treatments have been stumbled upon. So lithium treats bipolar disorder, that was a total accident.
But they've been using that since Roman times.
Absolutely, total accident they found it. Aspirin, discovered pretty much by accident.
Looking a willow bark.
Yeah. A lot of things discovered by accident. We know it works, and it has certain benefits, but we don't know exactly how it works. I said we have absolutely no idea. We've got some hints as to how it might work, but the mechanism is uncertain. We do know that it reduces hepatic gluconeogenesis. So that means we get a reduction in glucose release by the liver, so that reduces the hyperglycemia. And the hyperglycemia is one of the things that causes a lot of damage in type 2 diabetes. It has some effect on increasing insulin sensitivity as well, not a huge amount. We don't know exactly how it works. We do know that it seems to activate AMP kinase. Now, I mentioned AMP kinase in the last lecture. AMP-dependent protein kinase. When your levels of ATP in your cells are depleted, your cells make more ATP by taking 2 ADPs, reacting them with protein kinase, and making 1 ATP and 1 AMP. The amount of AMP in your cell is an indicator of the metabolic state of that cell. If you have a high level of AMP in that cell, it means that cell is quite energy depleted. Which means that what you want to do is do more glycolysis, so generate more ATP. So AMP kinase promotes glycolysis over gluconeogenesis. Okay? So if you activate AMP kinase, you'll reduce gluconeogenesis, increase glycolysis, and reduce your blood glucose levels. It also seems to inhibit the transcription of gluconeogenesis genes. And we also know that activation of AMP kinase stimulates GLUT4 trafficking in the muscles. There's good reason for that. If you're doing intense exercise, your muscles are going to be depleted of ATP, which means their levels of AMP are going to go up. AMP kinase will be activated, and your muscles will traffic GLUT4 to the surface to try and get more glucose into them to try and increase its ATP production. So activation of AMP kinase seems to stimulate GLUT4 trafficking in muscle cells, and that might alleviate some of the insulin resistance in type 2 diabetes, i.e. increased insulin sensitivity. But we're not absolutely certain. This, incidentally, might be one of the reasons why people like sumo wrestlers who exercise intensely but are very overweight don't have type 2 diabetes. If you do a lot of exercise, you're going to be metabolizing all these fat stores that are in your muscles. So you'll reduce the amount of lipid in your muscles. So you'll reduce any kind of insulin resistance you might get. Once sumo wrestlers stop training, they all get type 2 diabetes. So it seems to be related to exercise. Possibly to do with AMP kinase. That is activated by high levels of exercise. So this is the little diagrammatic representation. Activation of AMP kinase reduces gluconeogenesis. And it also causes some change in transcription of genes. It seems to possibly inhibit P10 as well. And P10, remember, will catalyze this reverse reaction of PIP3 to PIP2. So if you inhibit P10, you'll have more PIP3, more activated AKT, and more insulin signal. So we have got various different ideas about how metformin might work. Seems to act on the signaling pathways that are inhibited in type 2 diabetes, not absolutely so. GLP-1 agonists are the new sort of holy grail treatment of type 2 diabetes. Well, not the holy grail, but they're a very attractive drug type. Remember, GLP-1 is a gut hormone, also called an incretin. It's secreted in the ileum in response to nutrients and causes secretion of insulin, or enhances secretion of insulin, only when blood glucose levels are high. Therefore, it's a very good therapeutic because it's impossible to overdose on it. You have no danger of hypoglycemia. So, blood glucose goes up, ATP goes up, ATP channel closes, blah, 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 insulin secreted. GLP-1 binds to its receptor, activates the G proteins, increases levels of cyclic AMP, and this binds to and activates protein kinase A and EPAM2. And these enhance insulin secretion. But they only enhance insulin secretion if the KTP channel is closed, if blood glucose levels are high. So anything that binds to this receptor and activates it will enhance insulin secretion. That's what a GLP-1 agonist is. Okay. So I've talked a lot about dietary risk factors for type 2 diabetes. So now I'm going to talk a bit about some genetic risk factors. Remember, no genetic cause, only risk factors. Most are SNPs, single nucleotide polymorphisms, and there are many of these, hence a polygenic disorder. Currently one, and there are multiple ones that contribute to the disease. Some of these are genes for the KTP channel. Don't bother memorizing these. But the KTP channel consists of two proteins, one called KTJ11 and one called ABC68. Don't worry about that. So anything that affects the functioning of the KTP channel is going to change the glucose response in insulin release. Change glucose dependent insulin release. So it may mean you need to have a higher level of blood glucose to release, cause insulin release, if you've got a mutation in this channel. Similarly, a protein that regulates glucokinase. Remember, glucokinase is the first stage in glycolysis in pancreatic beta cells. So it controls pancreatic glucose sensing. Mutations in this can be contributing factors to type 2 diabetes. Zinc transporter 8, got no idea what that's a risk factor. But it is. For most SNPs, we don't actually know the molecular reason why they're risk factors. But we do for these two proteins. Because these are part of the glucose sensing pathway, part of the signaling pathway whereby blood glucose is sensed and insulin is secreted. So if you mess up that, you mess up insulin secretion response to high blood glucose and you cause contribute to diabetes. Some mutations in the KTP channel make the KTP channel less sensitive to ATP. Therefore, you need a higher blood glucose level to trigger insulin release. Makes you prone to hyperglycemia, and hyperglycemia can cause all the other problems that you get associated with type 2 diabetes. So it really sort of gives you, if you like, a head start in developing type 2 diabetes. Some of these mutations make the KTP channel sensitive to free fatty acids. So again, it means you're more likely to get to type 2 diabetes if your free fatty acid levels in your blood are high. So free fatty acids can make the KTP channel less ATP sensitive. Therefore, excess free fatty acids in the blood lead to hyperglycemia. And if these mutations make the KTP channel more sensitive to free fatty acids, then you're more likely to get type 2 Some of them we know the molecular reason, many of them we don't. Okay, so last slide on type 2 diabetes before we have a couple of slides on monogenic diabetes, which is this. What is more important, genetics or lifestyle? And there are some clues from history. I'll leave you to make up your own mind as to which of these two. All we have is evidence. We don't have any proof. Genetics or lifestyle. It's very, very difficult to tell what's the most important ingredient in a cake. You don't have any. If you leave any of the ingredients out, the cake won't work properly. So you'll find out by what you bake on time. It's obviously a combination of genetics and lifestyle that contributes to type 2 diabetes. But this is a very interesting graph. Okay, this is the new cases of diabetes in Amsterdam and Utrecht over a 15-year period between 1935 and 1950. Look at the cases of type 2 diabetes between 1941 and 1945. What's happened? They've gone through the floor. There are almost none. What happened during this period? War, Second World War. Food in the Netherlands was very scarce. The Nazis were in charge. They didn't think that much about feeding the populace. And levels of type 2 diabetes massively went down. So very calorie restricted people aren't getting type 2 diabetes. Well, that's a very good question. How accurate is that data? How much did the Nazis care about recording cases of type 2 diabetes in the populaces that they'd subjugated? Probably not very much. So again, clues. But be very careful whenever you see this data, as people are already asking the right questions about this. I've got high hopes for you all as scientists. Always question the data. Okay. What's type 2 diabetes caused by? Lifestyle, genetics, luck, McDonald's, or a combination of many factors? Who thinks E? Yes, good, that's the answer. That's what we think, a combination of many factors. There is some luck in it. I mean, your genetics are luck to start off with, but there's always some luck in developing a monodysis. Right. However, there is no luck apart from your genes in these forms of diabetes. Monogenic forms of diabetes, an monogenic disease, is a disease that if you have the mutation that causes it, you will have it. Every single person has the delta F504 mutation, has in the CFTR gene, has cystic fibrosis. Similarly true of monogenic forms of diabetes. I'm going to talk quite briefly about them. Let's talk about not this one first. We're going to talk about MODY first. Maturity onset diabetes in the young. It's caused by several different gene mutations. This is non-insulin dependent diabetes. You don't have insulin resistance, usually presented before the age of 25. So generally, you don't have diabetes when you're born, but you develop diabetes before the age of 25. It's caused by one of many mutations. 80% of cases are mutations in one of two genes, either glucokinase or HNF alpha. Glucokinase, as we know, is the glucose sensor. This diagram you know very well now. Higher glucose concentrations are required to get insulin release, so you get mild hypoglycemia and you get development of diabetes. You can control this by diet. Some people go on to the insulin therapy. HNF1 alpha or 4 alpha is a transcription factor. Patients with these mutations tend to have more severe symptoms. We don't really know why it causes diabetes, but we do know that the problems are usually with the release of insulin rather than insulin action. No insulin resistance, there's a problem with insulin release. Pancreas is intact, you've got your beta cells, they've got insulin in, they're just not coming out. And for that, sulfonylureas are a very good treatment. They're an effective therapy because they trigger insulin release at the pancreatic beta cell directly. Okay. That's Modi. Neonatal diabetes, the disease I actually worked on early on in my career. And we were part of the lab that first examined the genetics of the patients that had neonatal diabetes. So people with neonatal diabetes are born with it. It manifests from birth. It was originally thought to be a type of very early onset type 1 diabetes. Patients treated with insulin. When I say patients, we're talking about babies, newborns. Taking care of a newborn baby is difficult enough without having to sample its blood glucose every hour or so and inject a newborn baby with insulin to try and maintain its blood glucose levels. Very, very distressing for the parents, very bad for the children because their blood glucose levels are going up and down constantly. However, it was discovered these patients have intact pancreatic islets. So they don't have type 1 diabetes. They still have their pancreatic beta cells. They still have insulin. They're just not releasing it. So the question is, what's going on? And what we found was that these patients have mutations, single mutations in the genes of the KATP channel. So the KATP channel was always open. It was not closing in response to high blood glucose levels. So this bit wasn't happening. That KATP channel was never closing, which meant that all the things downstream of it didn't happen. No insulin was being released. What we found was, when we took these channels, which were mutated in these patients, and we tested them in the lab, we found that they could be closed by sulfonylureas, which meant that when these children were put onto sulfonylureas, which were already a licensed drug, so you're allowed to give them to people immediately, they had perfect glycemic control, they didn't have to have insulin, and they go on to lead normal lives. Some of these patients also have some neurological problems because the KATP channels are present in neurons, so they have some neurological deficits. So this is an example of how work that we do in the lab, the sort of work that you're going to do in your level 3 projects, might seem far removed from many patients. But simply doing stuff in a lab within isolated cells, like we did here, based on genetic information taken from patients, can lead directly to a cure for a disease. Not many people have neonatal diabetes, but to the people it has, this has made a gigantic difference. Let me give you an example of that. This is a boy who has neonatal diabetes with neurological complications. He's 3 years old. This is in a birthday party. He has a very weak neck. He can't sit up properly by himself. He's a bit listless, not interacting very well with his brother. He's generally not in a very good way. He's never walked and spoken. We analysed the channel, the potassium channel, the KATP channel in this boy. It's not in this boy. We had a DNA sequence and we found out what the problem was. We found the channel was sensitive to sulfonylureas. This boy was put on sulfonylurea therapy. This is 3 months later. See the difference. He stands up, walks, he's interested, he's alert, chases a football, interacts with the camera, and he's speaking. This is the difference, the stuff that people do in labs can make to real patients. Always worth bearing that in mind. Might seem slightly divorcing when you're staring down a microscope for 12 hours a day, but you can really make a difference by research. Okay. That's it. Summary. Type 1 and type 2 diabetes both have genetic, environmental, and lifestyle components. Type 2 diabetes occurs when metabolic compounds include the normal insulin pathways, for example, insulin secretion, insulin receptor pathways. So remember, all we're talking about is how signaling pathways that we've discussed are aberrantly manipulated in certain diseases. And by knowledge of that, we can work out how to treat the people who have these diseases. Right. Now, next week is a tutorial. Okay? The tutorial is going to be on a paper analysis. Okay? So it's not going to be a lecture, we're going to be doing some group work. Paper analysis is your coursework. Most of you will never have done this before. It's absolutely vital that you come to this if you want to get some idea about how to analyse papers. People need to sign the register as well when you go. You've got to hand that around. Right, I'll put it on the end here, you can come and sign it as you need. Now, please come along to that. I have posted the paper online, it's on Blackboard. I've also posted a sort of schedule for the tutorial. Okay? This will give you some pointers to think about when you're reading the paper. It's about insulin resistance. It directly relates to what we've been talking about. It's about insulin resistance and inactivity. Please look at the paper. Please read it. Print it out and bring it with you. Please think about the questions on the tutorial schedule. And next week I'll divide you up into groups and we'll have a big discussion about how we analyse this paper. We'll look at the coursework brief and work out if this was the paper for your coursework. If it was, how would you go about writing this report? So it's really important you come along. I won't be recording the session because there's no point recording a session like that. Okay? So please come along to that, engage with it, and if you do that, I'm sure you will do really well in the course. If you've got any questions about the paper over the next week, please email me. I'll do my best to answer.